Okay, these are the solutions to thermodynamics 1. And again, I want you to use this as a check more than just copying down the answers. Just copying down the answers is not helpful to you. You will not know the information. It's no way to memorize things. It's no way to learn things or practice things. Please use this to check work that you have already done, not to copy down work for the first time. So, 4 assumptions we made in developing the kinetic model. So for our kinetic model, we say Newton's laws are obeyed. Which is good. We want to be able to follow with all of that. All particles are the same size. Or the same mass. We also want to say that they collide elastically, so there's no energy loss in collisions. Everything transfers cleanly. And then the last thing is that there are no intermolecular forces. They're not sticky. They're just hard elastic balls that do not stick to each other. They hit and bounce off every single time. We use the kinetic model, and I'm not going to write this down, you can listen to it. We use the kinetic model because it is convenient to talk about heat transfer in these terms if we can simplify things. So all of this is a simplification, because it lets us visualize what's happening a little bit easier. Because when we look at sort of this particulate model of matter, it can get very complicated very quickly because we're talking about a whole lot of little things. But if we can take a solid and imagine that inside of that solid we just have a lot of little balls bouncing around, or same thing with a gas, and look at heat transfer and pressure and things like that in terms of those little balls, it makes life easier. So, in terms of the kinetic model, define heat. So, heat, and this is the important part for heat, is the sum of all kinetic energies of all particles in a substance. So what's important is that heat is the sum. We're adding everything together when we talk about heat. And because heat is a type of kinetic energy, we're going to use joules as we talk about heat. But it's adding up all of the kinetic energy that we have in there. Temperature is different. Temperature has to do with the average kinetic energy of the particles in a substance. So it's the total heat energy, the total heat that an object possesses, divided by number of particles in that object. So what's really interesting about this, since heat is the sum and temperature is the total, if you had a pool of cold water, and then you had a coffee cup of hot water, your pool would have more heat than that cup of hot coffee, because there are more particles in the pool, and heat is the sum. So there are more particles to take the sum with, so we're going to get more of that thing we're taking the sum of. However, the hot water is going to have a higher temperature because the individual particles in the hot water, on average, are moving faster. They're more energetic than the individual particles in the cold pool. Describe in terms of the energies of individual molecules what happens when an object gains heat. The molecules gain more energy, and because it's kinetic energy, it means that the individual molecules on average move faster than they did before. Adding heat to a substance makes those molecules jiggle around and bounce around with greater speed. That's having more energy. What was the original unit for thermal energy? Well, what we used for that originally was the calorie. How is that unit defined, and how is that unit used today? A calorie is the energy to heat 1 gram of water by 1 degree Celsius. Today we use calories, or specifically kilocalories, as a food energy measurement. So the 1 calorie that you get from food is actually enough heat to raise 1,000 grams of water. So 1 kilogram of water by 1 degree Celsius. That's a food calorie. It's a lot of energy. What is absolute zero? This is the temperature at which the average kinetic energy of particles is zero. So it's so cold nothing moves. And one of the things that's important to realize about this is that we have gotten close, but it's almost impossible to reach absolute zero. We get really close. We've gotten like 1 times 10 to the negative 4 Kelvin. So super close, 1/10,000th of a Kelvin. So 1/10,000th of the way there. But it's really hard to make the energy of particles completely disappear. And that's what happens when we're talking about absolute zero. What's the temperature of empty space? So the temperature of empty space is sort of the background radiation. This is measured at 3 Kelvin. Not negative 3 Kelvin. 3 Kelvin. So 3, where Kelvin is that absolute temperature scale. It's not zero. There's still stuff in space and it's still moving, but it's not moving very fast. This is really cold. This is roughly negative 270 degrees Celsius. So looking at our temperature scales, the Kelvin scale is absolute, meaning the lowest that we can get is 0. Degrees Celsius, 0 degrees is freezing water. And then Fahrenheit, degrees Fahrenheit is just weird. (32 degrees Fahrenheit is freezing H2O. It can get colder than 0 degrees Celsius. It can get colder than 32 degrees Fahrenheit. It cannot get colder than 0 Kelvin because it is the absolute lowest possible temperature that you can have, 0 degrees Kelvin. Is heat kinetic energy or potential energy? Nope. I apologize. I just wrote down the last thing. Heat is kinetic energy. Heat is the energy of motion of tiny particles. That is a type of kinetic energy. It has to do with motion, so it's going to be kinetic energy. Define the term pressure. So pressure is force per unit area. A gas exerts pressure on its containers, the way that we talk about it using the kinetic model. Pressure is the force of collisions with the container, or whatever we put in there. So looking at the little particles bouncing off the wall is what gives rise to what we have as pressure. So because of that, the ways that we can increase pressure of this 1 liter of an ideal gas. And again, if pressure is the force of collisions with the container, we need to think of ways to increase the number of collisions, and then we need to increase frequency of collisions. And we need to increase the force of those collisions. So, increasing the number of collisions, one of the ways that we can do that we can shrink the volume. Shrinking the volume is going to increase the pressure because we're going to get more collisions with our surroundings now. Another way that we can do this is to increase the temperature. What that does is it gives particles more energy. And the two things that more energy gets us, we get more force in our collisions and we get more frequent collisions. The other thing that we could do is we could add particles. We could put more gas inside of this 1 liter container, and adding particles is going to increase the number and possibly the frequency of collisions. So those are 3 ways that we could increase the pressure of an object in terms of the kinetic model.